Hi there, guys. Well, welcome back. We are about to work on the examples, which are building up towards exercise 2R in the HLAA Oxford coursebook. This is dealing with rational functions, and in particular, rational functions which are linear function over a linear function, and rewriting them as reciprocal functions, and then considering the transformations from the original reciprocal function, 1 over x, which will take you to the equivalent reciprocal function which you have for the rational function. A lot of words there, but it will become straightforward when we go through all of this. Essentially, have a little look at this. So we're talking about this. We're saying, let's take this rational function, let's make it look like this, and let's consider how do you take the original reciprocal function to this reciprocal function using transformations. That's the basis of this. Now, this is actually bringing together a lot of ideas, and in particular, we're going to need to put to bed this idea of doing two transformations inside the bracket, so two transformations in the x direction. So what I'm talking about here and why I've written that down is I'm basically saying, here's my f of x, and in order to get f of x looking like this, the transformations required are these. In other words, I'll need to replace x by b of, in brackets, x minus h. I'm going to need to times that 1 over b x minus h by a. So we're timesing by a, and then we're putting a plus k on the end. You can see that that's 4 separate transformations, and we definitely need to think about the order of these ones here. Okay, so before I actually go into this, I'm going to spend a little time explaining the note which they actually put on the end of this exercise. So on page 145, they come up with a nice little hint, which, to be honest, I would like to have seen earlier on. But the hint is this thing here says, you have seen in the examples that if you want to transform a function y equals f of x to y equals f of ax plus b, factor out the a, factorize, take the a out as a factor, and then stretch horizontally, they're saying dilate, same thing though, stretch horizontally by a factor of 1 over 8 and translate horizontally by b over a. Now, if you like to remember statements like that, which all seem pretty dry, and don't like to think about the structure of that too much, or if you can just deal with that, if you've dealt with it before and you've learned it well, then you can skip about the next 5 to 10 minutes of what I'm talking about, because I'm going to talk through that point. Okay, that's a really critical point, and that transformation is likely to turn up somewhere in your exam papers. When I say transformation, I mean set of transformations. Okay, so let's finally put this to bed after talking about this a couple of times. I'm going to build up to f of 2x minus 90. Now I've put in already my f of x is equal to sine x, and I'm just going to start off by saying, here's a transformation which is a stretch of 1 over a, or in other words, 1 over 2 in the x direction. And you can see that my purple graph there is a squash of a factor of 2, or a stretch of a factor of a half from the red graph. We're seeing, so let's just take this one. So let's take this here. Okay, and we can see that, our normal points on the red graph on sine of x, which is the red graph here, are going to be taken twice as close into the x-axis. And so we can take this point as well, that's going to go twice as close in. Okay, so if you were going to do f of 2x to f of x and consider the transformations which take you from the purple one to the red one, well, that's a stretch of a factor of 2, so scale factor 2 in the x direction. Okay, now the reason why I've written it that way round, you think, well, that's the wrong way round. If we wanted to take f of x to f of 2x, we now have to undo this. We have to go backwards through our transformations. So the stretch in this case, stretch scale factor, are half, or 1 over a if you like, in the x direction. So if we want to go from f of 2x to f of x, so the other way round to how we normally do things, we're normally saying, how is f of x changed to get to f of 2x? If you want to do f of 2x, f of x, things are the normal way round to what you would expect. We're taking values, so say for example for 45 degrees, when I put 45 degrees in here, we're taking values which are from twice as far away on the normal f of x graph. So when I put 45 degrees in here, I'll get f of 90, and f of 90 is saying sine of 90 degrees, and sine of 90 degrees is my height of 1, and so that's what I'll plot when I put in 45 degrees. Okay, so it's taking values which are from twice as far away on the original graph. Okay, so that's why it's working backwards. Okay, and we're going to do the same thing with just a let's do x minus 45 there. We'll do the same thing with a translation. I'm just doing the single case in this version. And similarly, here, if we wanted to go from f of x minus 45 to f of x, well, that's the normal way round. So f of x minus 45, that's the purple graph here. We're saying, well, let's take away 45 degrees. Okay, let's move this thing backwards. So in order to get to the red graph. So we're saying that this would be a translation by the vector minus 45, 0. Okay, and the reasoning behind that again is saying, well, I don't know, if we put in, say, for example, 90 degrees for x, then at 90 degrees, we're going to be plotting the value from 45 degrees ago. So take away 45 degrees, and taking away 45 degrees gives us 45, in fact, and then put that into the original function. That's giving us a height of square root of 2 over 2. You might remember that from your special ratios. You might not. You might see that later on. And we're going to plot that height where we are now, root 2 over 2 there. Okay, if we take 135, we're going to take 45 degrees off that. So we're now putting 135 in there. Take 45 degrees off there, we're getting 90 degrees, and f of 90 degrees is here. We're now plotting that when we put in our 135. Okay, so hopefully that's relatively straightforward there. So now obviously if we're doing it the other way around, which is what we want, we're saying what's the transformation from the original function to f of x minus 45? Well, we'll need to do that backwards. So that's going to be our translation, and the translation of 45, 0. So we just need to do that backwards. We're going to take this graph and go forwards by 45 degrees in the positive x direction to get to the purple graph. Right, I hope that that is all really obvious and you've seen that before, but that's the reasoning why. Okay, so building it up then, we're going to talk about two things here. We're going to talk about 2x plus 90. Okay, so we're going to deal with this one. Not plus 90 rather, we'll do minus 90, okay? So we can deal with that one, and then I'm going to put this in brackets. I'm going to say 2 of x minus 45, and we're going to think about why this is working. Okay, so okay, let's take that. Okay, now in this case, if we're going from f of 2x, I'm going to take it forwards again, f of 2x minus 90 to f of x, forwards, backwards, whatever we want to call it. I'm going to take it from my transformed function to my original function. That's not the normal way of doing it, probably backwards, okay? But we're going to take it this way round. So let's take, again, we've got this purple graph. Let's say, for example, let's put in 90 degrees in here. So in 90 degrees, we're going to need to start by doing 2 lots of 90 minus 90, or 2 lots of 90 is 180, and then minus 90, oh, it also takes us back to here. So I'm going to plot f of 90, and f of 90 is here. I'll plot the same point at that point. Okay, so that one was pretty boring, to be honest. So let's take this point here. So let's take 135. Okay, so let's put in 135. Now, when you put 135 into 2x, you're going to get 270. So 135 is doubled, is 270. Minus 90 gives us 180. And if we put in 180 into here, into f of x essentially now, we're going to need to plot this height here because we started off by putting in 135. So at 135, we plot a 0. Okay, so how did we get that? Well, we doubled the distance and then we went back by 90 degrees. So if we want to take any point on the purple graph, we need to say, well, this is a stretch of factor 2 in the x direction. Okay, so x direction followed by, I'm going to get rid of the x direction, okay, just to fit it in. So stretch by a factor of 2 in the x direction, and then it's a translation of 90 backwards. Okay, so going backwards 90. Okay, so that's taking all of the purple points and plotting them onto the red points. Okay, I could do that the same for, let's take this one here. Okay, so at 0 degrees, what are we going to do? We're going to, let's take this point here. Okay, so if we double 45, we get to 90, and then we're going to take that point back to here. If we're going back to f of x, by taking away 90, we're now going to plot it there. So I'm doing this whole thing backwards here. Right, so if you followed that, then f of x taking us to f of 2x minus 90. Well, we need to undo these transformations by, first of all, undoing this and then undoing this. It's a bit like when we solve 2x minus 1 is equal to, I don't know, 10. When we're going forwards, x is saying, well, times by 2 and minus 1. And then when we're going backwards to actually find out what x is, we're going to plus 1 and then divide by 2. Okay, so we're going to do this in the reverse order. So we now need to do plus 90 to undo this one here. So we need to going to go forwards by 90. And then we're going to need to stretch by a factor of a half. So that's the undoing function, stretching by a factor of 2. Again, in the x direction, we should say. Okay, so there we go, right? So if we want to take f of x to this thing here, we need to do the translation first, which is not what you expect. When you're looking at this, you think, oh, maybe I need to do the stretch first. No, no, no. The thing inside the bracket is always the way around which you don't expect. So we need to undo the minus 90. So we need to make that plus 90. And then we need to do the stretch of a half, which is, again, is the reverse of what you expect and in the reverse order to what you would expect as well. Okay, so that really begs this question as to why they were talking about f of b of x minus h, I think they wrote. Why they're putting it in this format and not in this format, okay, where b and h are things which you can find. So why did they prefer to have a factorized version inside? Okay, so we're going to deal with that now. So let's check out this graph here. Let's put in here instead x minus 45. Now it's exactly the same thing as before. Okay, so it's exactly the same thing as before. I've just factorized that thing on the inside. Now let's take this one. Okay, so same graph, however, different thinking for this, different logic. So again, I'm going to do it backwards to start off with. I'm going to do the graph of f of 2x minus 45, x minus 45 in brackets takes you to f of x. What's happening there? So that's saying if I put in, let's say again, let's take this point again, 135, okay? So this time around, if I put in 135, okay, so 135, I'm going to need to take away 45, which is 90. And then I'm going to need to times by 2, which is 180. So that's different. That's a different process to before. It's a different order of doing things. So we're going to take away 45, and then we're going to double the 90 to get 180, and then we're going to plot that point there. That's what's happening. Okay, so 135 in for x gives us 90 there. 2 lots of 90 is 180, and f of 180 is what we're going to plot. F of 180 means sine of 180, so we're going to plot sine of 180 at 135 here. Okay, so let's just take some of that backwards. So what are we saying here? We're saying that, first of all, we need to do a translation of minus 45 on all of our points. So I chose one point there, but it works for all of our points. And then follow that by a stretch of a scale factor of 2 in the x direction. I should state that, but I've not got a lot of space. So if we do it the other way round again, nearly there, get this. This is a stretch of a factor of a half. Okay, we're undoing this first of all, and then we need to undo this. So by undoing that, we've got 45 forwards and 0 there. Now let's just stop and think about this. Okay, it's the same logic as before. So let's stop and think about this and just think, okay, well, in this bracket here, what you would expect to be doing is this transformation first, the translation. Even if you do it minus 45 or plus 45, you'd be expecting to do the thing inside the brackets first. But everything on the inside of the brackets works the wrong way around to what you expect. So in fact, it's the stretch first, and it's not a stretch of 2, it's a stretch of a half. And then it's the translation, which is a translation of 45 degrees in the x direction, in the positive x direction. Okay, so again, it's the wrong way around to what you expect. So that takes us back then to this question, I think we're on, or the note. So take us back to this. Let's just deal with this again, because we're really unpacking a lot of what is in this original expression here. So let's just colors there. And what I'm unpacking here is this. It says where A is a vertical dilation factor, B is the reciprocal of the horizontal dilation factor, H is the horizontal translation, and K is the vertical translation. I mean, I find that's really difficult to read through, and that's why I'm trying to unpack this. Okay, so let's just state the transformations here. We're going to take f of x to, now what did we say? We've got A, f of b, h minus x plus k. Now, I can do my horizontal transformations first and then my vertical transformations, because my horizontal transformations only act on the first part of the coordinate and the vertical of all of my coordinates in the coordinate set, and then we can do our vertical transformations after that, because they only act on the y part of each of the coordinates. Or we can switch them around. We can do vertical first, horizontal first, horizontal first, vertical first. Okay. But in this format, we definitely need to respect what's happening first in terms of stretches and translations in the x direction or the y direction. So I'm going to deal with this by dealing with the x direction transformations to start off with. So there's 4 transformations here, and I would say that this is, remember, the reverse to what you expect here. So we're dealing with the thing outside the brackets first. So this is a stretch in the x direction of 1 over b. That's the first thing that's happening. Second thing that's happening is a translation in the x direction of h0. So that's what we were talking about before. That's the second thing to happen, which is the thing inside the brackets, the opposite to what you expect. And then the third thing which is going to happen is now everything on the outside acts the normal way around. So we're timesing all of those heights by a. So now we have a stretch in the y direction by a factor of a. So scale factor of a. And then finally, we have this transformation at the end. We're saying once we've done all of that, let's add on k to all of our heights. And so we're getting a movement of 0k there. So a translation at the end. So that's how I would state those transformations. Okay, so if we can write rational functions like this, that's going to be the next bit. If we can write rational functions like this, then we can draw those functions by doing these transformations from our original 1 over x. Okay, now all that stuff I've highlighted in yellow is essentially this. They've done it slightly different. They've said where a is a vertical dilation. So they've done the a first, and it's fine to mix the order up, but as long as the stretch in x comes above the movement in x, and as long as, so the yellow one needs to be above this one here, and as long as this stretch needs to come above this translation. So it doesn't matter if we switch those around, as long as they're both above these two orange ones. So they're orange ones. You have to do those stretches first when we've got it in this format, by the way. Okay. Now, I think I probably didn't quite answer the question when I said, why do we use f of b in brackets x minus h rather than f of bx minus h, no brackets? And I think that's because it's easier to perform a stretch and then a translation than it is to do a translation and then a sketch. And then it's also easier if you can identify what your stretch is to then think, okay, I've stretched something out, okay, and then I've stretched something, and then I've made a movement. And so if you can see where that point has been shifted, then you can identify the function easier, because this thing here just becomes your movement from 0. That's perhaps not a great explanation. You need to see that through the questions. But it turns out that this is a more useful form to identify functions as well. Okay, right. So let's have a look at some questions. Well, let's have a look at some questions. Actually, let's have a go at doing what they're really talking about. Okay, so let me just snip a bit of something so I can just write on here. So, right, that's the first part of the teaching done. The second part is to say, okay, well, let's actually try and write one of these rational functions. I'm going to make one up here. I'm going to say, let's try and write 2x plus 4 over 3x plus 9. We'll try and write this one as a reciprocal function. Okay, now the way I'm going to do that, let's look at what the reciprocal function should be. We've got a over b x minus h plus k. That's what we're trying to get. And a is not an expression which includes x, so it's just a constant. So what I'm going to need to do here is essentially split this into two fractions, this part and this part, where the algebraic part is going to cancel in the second fraction. Okay. So in order to do that, I'm first of all going to take out my factor of 2 on the top. So I've got x minus 2 there. And I'm going to take out my factor of 3 on the bottom. So I've got x plus 3 there in the bracket on the bottom. And now I'm going to try and get a single denominator, because you can see there's only one expression for the denominator here. And I'm going to do that by forcing x plus 3 to exist on the top. And I can do that by saying 2 lots of x plus 3, okay, x plus 3 there. But then to make minus 2, I realize that I have to then take 5 off. Oh, I've changed the question to my question, but okay, that's fine. So x minus 5. Okay, so that's now going to give us the same thing as this thing here. Okay, plus 3 minus 5 gives us that minus 2. So I forced this to exist. If I want, I can put some brackets around that, and that's essentially what I'm going to do in a bit. And then I've still got this 3 and x plus 3 there. So now I can times out top. I've got 2 lots of x plus 3. And I've got 2 lots of minus 5 is minus 10. And now I've got that over 3x plus 3. So now I can essentially split this into 2 fractions. I've got this fraction and I've got this fraction here. So I can split that up a bit like I can split up 3 minus 1 quarters is the same as 3/4, take away 1/4. Okay, so that's what we're going to do. And when we split that up, we can see that this and this is going to cancel on the left-hand part. Sorry, that's just a bit aside. Just come over here. So we've got 2 divided by 3 left when this and this cancels. And then we have minus 10 divided by 3 over x plus 3. Now we have things in this form here. So we have essentially a is minus 10, a is 2/3, h is minus 3, and b is 3. Okay, but there we go. That's one technique for this. There are other techniques. So another technique would be a division of polynomials. Now, I know you've not done this yet, but you might be interested in it. So let's say, turn the pen. So let's say 2x minus 4 is to be divided by 3x plus 9. Obviously, you see that I've actually chosen nice numbers here. The 9 is dividing by 3 and the 4 is dividing by 2. You can still do this, the previous technique, in the same way, but you'll often get fractions. So this method, though, is going to give you just a guaranteed method every time, where you don't have to do a lot of problem solving thinking. Okay, so this is a division of polynomials. And in order to do this, we're going to say, we're going to divide this polynomial by this polynomial. This is a bit like long division. We're going to say, how many 3x's go into 2x? Well, 3's, that's essentially the same as 3's into 2. So, so yeah, how many 3's into 2? So that gives us 2/3. Okay, so that's basically saying this divided by this. That's really us doing 2x divided by 3x. Okay, and now I'm going to times this. It's just a technique, I'm not explaining this really, just explaining the process. So I'm going to times the 2/3 back by this. If I do that, I get 2x, which is what I wanted, and 2/3 of 9 is equal to plus 6. And now I take the difference of those two things. So this and this is going to cancel. And minus 4 take away 6 is going to give us minus 10. And so we can say that 2x minus 4 divided by 3x plus 9 is equal to 2/3. Okay, that's my answer for the division, with a remainder of minus 10, which is yet to be divided by 3x plus 9. We couldn't divide that by 3x plus 9. We can't do 3x into any x's which are left. So that's our remainder. And our remainder, like when we say, I don't know, 10 divided by 3, say 3's into 10 goes 3 times with remainder 1. Well, that's really 3 remainder 1, which is yet to be divided by 3. Okay, so that's this division which you've done in primary school leads you actually to mixed fractions, and that's essentially how I'm writing things here. Okay, so that's the same as this. That's like a mixed fraction, but I'm putting on my remainder is negative, so I'm putting on minus this thing. Okay, so that's exactly the same answer, and that turned out to be slightly less algebraic work if you just know this technique. Now, there might be another way. You might have been thinking, well, hang on, maybe I can actually do it like this. So I've got my 2x minus 4 there. and my 3x plus 9. And you can maybe say, well, let's equal that to a over b and x minus h plus k. And I'd expect as a higher level student, you might wish to play around with this to see if you can come up with your solutions for a, b, h, and k. So k is your x is your variable. And you can do that by setting this as an identity. And then you could multiply throughout by this, multiply throughout by this, and then you could compare coefficients on both sides. You should have the same coefficient of x squared, you should have the same coefficient of x, and you should have the same coefficient of x to the power of 0, or the same constant on both sides. Then you can set up 3 equations. However, you've got 4 unknowns. And I don't know, maybe it should be possible. Perhaps you can choose a clever value of x. Maybe there's a clever choice that you can make to give you a final equation as well. So remember that when you have an identity, it's true for all values of x. So say, for example, if you chose x equal to 2, then this whole thing is going to disappear here. So you could also choose when x is equal to 2, and you could hopefully that would give you a 4th equation. You could solve a system of 4 equations. Right. Okay. Now, if you don't know what I'm talking about there, fine. Okay, I'm going on a bit. But again, as a higher level student, I'd expect you to be thinking about these problems and trying to spend a page of algebra to see if that works or not. It might not, but you've learned something in the process anyway. Okay, right. Example 37. Let's actually crack on with these. Okay, so I'm probably going to go through these quite quickly here because there's a huge amount of examples and just lots of graphs. So example 37 says graph at each stage the rational function when y equals 1 over x is transformed by a horizontal stretch factor of a quarter, okay, followed by a vertical stretch factor of 3, and then a translation of -2, 3. And then it says state the transformed function. Okay, well, I'm going to state the transformed function first. Okay, so your transformed function is going to be, so the stretch factor of 4 is going to become, stretch factor of a quarter is going to become, because it's in a horizontal direction, that's going to be us saying 1 over 4x. Okay, followed by a vertical stretch factor of 3. Okay, so that now becomes 3 over 4x. And the translation of this thing here. So let's deal with the y first, because that's easy, plus the 3 on the end. And then we need to go backwards by 2. So remember, we can put on those brackets there at the bottom, and then we can put that plus 2. So that's what we need. And again, if you want to write that in the f of x form, you could say, well, that's going to be f of 4x plus 2 plus 3 times by 3 there as well. Remember what's happening there? That's a stretch of a quarter. That's a translation of -2 in the x direction. And then it's a stretch of 3 in the vertical direction. And then it's plus 3 in the vertical direction as well in the y direction. Okay, so that's my formula. Just going to check that one just in case I made a mistake. Yeah, there we go. There's the formula of 3 over 4x plus 2. 3 over 4x plus 2 plus 3. Yeah, okay. Now, I'm going to do this one on Desmos because there's just so much drawing to do there, okay? And so I'm going to do it on here. Obviously, in an exam situation, you have to get quick at sketching, so you're going to have to get used to that. But let's write down, we've got f of x equals to 1 over x. What do they actually ask us to do? They say graph at each stage the rational function when it's transformed by. Okay, so stretch factor of a quarter is going to be our new graph. Let's just write a new graph for this one. This is the next one. That's going to be 1 over 4x. Okay. Now, by the way, let's just look at the 1 over x graph. Just to sort of add in a little here. Okay. Just take that back a moment. You should be able to draw this graph really quickly. And by the way, it's really important that you do go through the point 1, 1. Okay, don't just draw 2 two curves randomly. It has to go through the point 1, 1 here. So you're going to need to define this somehow to show these transformations somehow. And you note that there aren't any axis intercepts. So it won't necessarily be clear what your transformations are unless you take coordinate points. Now it has to go through that point, and it has to go through this point as well. So I would label a couple of points as well. Right, as well. If you want, you could label other points. For example, we've got 0.5, 2. Okay, so there's a coordinate point as well. So, okay, so there's our original set of points. Now, if we want to come up with our first transformed function, we're getting 1 over 4x. Okay, and what's happening there? Well, we're bringing all of those coordinate points in. So, for example, the coordinate point 1, 1 is now the coordinate point 0.25, 1. So that's our transformed point. Okay, and we might want to just label a point there to be really clear with the examiner. Okay, so that was the first transformation. And then the next transformation was a scale factor of 3. Now I can't remember. Scale factor of 3. Okay, in the x direction. Okay, so we now have a third function. We could call it F1, F2, F3 with subscripts if we wanted to, but I can't do that here. So h of x is going to be 3 lots of the thing above, so 3 over 4x. And now you can see that the coordinate point 0.25, 1 is now going to be 0.5, 3. So that is my new graph there, and annoyingly it's done it in red as well. Zoom in a bit to see what we've got. Okay, so we've now moved from the green point. Let's take the other points away. Okay, let's take these points away to see what's going on here. Okay, so we've moved from the green point to the black point to the blue point. Okay, now we're going to do the next one. So the next one, I don't know, what can we call this one? Does it allow us to call something J of? No, it doesn't like J. Okay, might need to call this f of x again, okay, but it's not the original function. So f of x is equal to, and now the next bit was the horizontal translation, so we have 3 over 4 in brackets x plus 2. So that's now taking our coordinate point backwards by 2. So 0.25 is going to become minus 1.75, 3. Okay, so now we've gone there, we've gone to that purple point. And so the final part of this, right, this is f of x again. This doesn't like me writing other types of thing. Okay, so f of x is going to be equal to, we have this thing again, copy that, times it is that, and then it was, I think, plus 3 on the end as well. So I'm going to have to zoom out for this one a bit. Okay, so zooming out for this, and we can see that the coordinate point is now becoming minus 1.75, and we're adding 3 onto the y, so we're now getting 6, and so that's on our new graph, on our black graph there, and that's the final one. Right, you may have to find where the asymptotes are for that, and the asymptote you can see is at minus 2. So we're going to put in here x is equal to minus 2 as an asymptote, and you've also got y is equal to 3, which I can just see from the graph. I'm not doing anything fancy there. Okay, yeah, so there we go. I mean, it's a total mess, right? And that's why you can imagine me doing it sort of with my E-pen on here is going to be extremely difficult. So, and likewise, you have that issue of how do you lay all of this out? It's really, really difficult to do. Okay, well, let's have a look at the next question. We've got example 38 here, and it says, consider this function y is equal to minus 2 over 5x plus 10, and then plus the 1 on the end. And the first part of the question says, state the domain and range of the function. Now, with all of these reciprocal functions, they are essentially going to be shifts of this function in some way. So shifts in translations, stretches, and you're going to get essentially the same sort of shape to these functions. So it may be that that's reflected, it may be that it's stretched, it may be that it's translated, but you're going to get a horizontal and a vertical asymptote in these cases. Now, that's when, again, reminder, that's when we've got rational functions as well, which are equivalent, where you have a linear function over a linear function. Now, so when it says state the domain and the range of this function, we're simply saying, well, x can be any number can go in, any real number, but there's a vertical asymptote which it can't be, and that's when the denominator is equal to 0. And we can see that -2 is going to make that -10 there, and -10 plus 10 gives us a 0. In other words, we're solving 5x plus 10 equal to 0. So we know that the vertical asymptote is equal to -2, so we cannot include that in our domain. And likewise, in terms of our range here, we've got a horizontal asymptote. So again, the range can be any number you choose, apart from, apart from the fact that this can't be equal to a 0. It can't be equal to a 0 because it doesn't have a 0 as the numerator. The only way to get a 0 out of fraction is if you have a is equal to 0. Okay, and we don't have that, so we can only tend towards 0 by putting in really, really large numbers on the bottom. So we can't get a 0, which means that when we, after adding 1, we can't get a 1 either. So we can't get a 1 out of this function because we can't have a 0 here. So that means our horizontal asymptote, see I've made a mistake, y rather, can be equal to 1. So our horizontal asymptote is y equal to 1. Okay, so there's our domain and there's our range of these functions, or this function. It says, then it says state the transformations in an appropriate order. So that are performed on the graph of f of x equals 1 over x to obtain the graph of the given function and describe the transformation. Then the final part says graph the transformation at each stage and check your final graph against the graph of the given function. Yeah, okay, well, again, I'm going to do that on Desmos. Again, it's going to be really fiddly to do that here. Okay, so our transformations. Now, in order to keep it consistent with the way in which we've been approaching this before, I'm just going to change this. I'm just going to say that our function here, so actually let's say that the original function, 1 over x, because that's what they define here, and our y is going to be equal to -2 lots of f of this thing here, 5x plus 10 of our denominator, and then plus 1. So that's what's happened to f of x in order to get y. Now, again, as I was saying, to be consistent with before, I'm just going to write it round so that I've got the 5 and x plus 2 there. So factorize on the inside, put the plus 1 there. And that way it makes our stretches come first. Both of our stretches come first. So now it doesn't really matter if you say we could have a vertical stretch. Okay, so we can do it vertical first of all, vertical stretch of -2. I should really say factor of -2, I'm just sparing myself a little writing. Vertical stretch of -2, and then a vertical shift of, translation rather, of 0, 1. And then we've got a horizontal stretch. Okay, we've made the horizontal stretch come first because we factorized it. And again, what happens on the inside is the opposite to what you expect. So the thing outside the brackets happens first. So horizontal stretch of 1 over a, which in this case is 5. So 1 fifth, and then followed by a then so we can see times there if you want, times by -2, and then followed by this horizontal translation of -2, 0. Okay, now it depends what you want to do. You can say this is the first thing, this is the second thing, this is the third thing, this is the fourth thing. Or you could switch it around. You could do the horizontal ones first. You could say horizontal, horizontal, 3, 4. That would be fine as well. Or you could say, I'll do my vertical stretch, and then I'll do my horizontal stretch, and then I'll do my vertical translation, and then I'll do my horizontal translation. As long as the translation comes after the stretch in that direction. Okay, so all of those are fine. Now, it might be that you actually combine the two translations as one vector. Instead of writing this and this, you could just say -2, 1. Okay, so you could come up with that translation as well, translation by that vector. So that's possible as well. So you could say here 1, 2. You switch around the order of 1 and 2, but as long as the translations come last. Okay, now that's easy to remember, but you then have to remember if you're going to make the translations always last in your transformations list, then you have to do the factorization inside the brackets there. Okay, let's have a look at what they write. So they're saying make a stretch in the x direction. Here we go, stretch, horizontal stretch of a factor 1/5. And then they're saying horizontal translation. Okay, and then they're saying vertical dilation or vertical stretch, factor 2, dilation stretch, they're saying now. So it's fine to say vertical stretch, factor of 2, and then comes the vertical, then it comes the vertical, oh, am I missing something here? Vertical translation. Oh, hang on a second, I think I'm missing something. There's a minus in there. Oh, there was a minus in there. Oh, yeah, but that's fine. Okay, but in me saying a vertical stretch of -2, that's still fine. I'm allowed to do a vertical stretch of -2. That just means to say that all of my heights are going to be twice as far away and then reflected in the x-axis. So they've split that into 2. So when they've come to the vertical stretch, they've said we've got the vertical stretch of 2 and then a reflection in the x-axis. And that's completely fine to do that. In fact, that's probably better. But a vertical stretch of -2 makes sense as well if you can do that in one go. That is fine. Because, I mean, remember, let's just get rid of all of this. Remember, when we're talking about stretching by scale factors, you know, if we have an object there and an object over here and an object over here, and an object here, we can say, well, if this is our original object, okay, then our image over here is going to be a stretch about this point here by a scale factor of 2, for example, if that's twice as far away. But if you now go backwards on the other side, so this is 1, this is 2, if you go backwards on the other side here, then you could say, well, this is my stretch of a scale factor of -1, and this is my stretch of a scale factor of -2. It takes it to the other side. And that's the same as what they're talking about here. They're talking about, sure, a stretch of a factor of 2, but then a reflection as well about the x-axis is what we've got. Now, we're used to this from previous courses, or at least we should be, the fact that we can do stretches of negative scale factors. Okay, right. I'm just justifying the fact that I'm not wrong, but it's nice that the fact that they have split it into 2. Right, okay, let me just write this one down. I can do it on Desmos, okay, just so I don't forget it. And so on Desmos, let's bring this back to here and see, I actually had to pause up a bit. Right, there we go. So actually, let's just go to a new Desmos tab. Okay, so again, we're starting with our original function. Let's say f of x is equal to 1 over x equals 1 over x. That's our original function. And then again, I'm not going to write g of x, h of x, and so on, because I'm going to run out of function. I'm just going to keep calling these f of x, although they're not really that. So we're going to do f of x is our next one, would be, let's say, do the horizontal stretch. So there we go. It's going to take it to all of the x numbers are going to come in by a factor of 5, or in other words, a squash of a factor of 5 or a stretch of a factor of a fifth. That's because we're substituting in for x, we're replacing x really by 5x. Let's find that out. Let's just say that that's the same as doing f of 5x. It's the same thing. Back to f. And no, it's not the original function, but there we go. Limitations of Desmos. So f of x, now our next function would be to say, let's do 2 divided by fx. Okay, and you can see how nasty this is to draw. And now we need to do our horizontal translation. Now remember, we wrote it in brackets on the bottom. So we said x plus 2. So we changed the function from f of x, 5x plus 10 to 5 in brackets x plus 2. And that was because we wanted the stretch to come before the translation. So now we're dealing with the translation of 2 backwards. And the final step is going to be to say that thing again. So let's just copy that. And then we had a plus 1 on the end. Nope, I'm missing something, aren't I? I'm missing something because I'm missing something because of that minus 2 again. Sorry, I'm missing this. So let's just get rid of this again. So the way in which they do it in the book is they do these 2 steps. We split the steps in 2. So they've done the scale factor of 2 stretch in the y direction, and then once we've done this one, copy this, copy that. Sorry, then they've done the minus there, so it's taking all our positive values and making them negative, all our negative values making positive. In other words, a horizontal, a reflection over y is equal to 0, or reflection about the x-axis. And then after that, we had translation. So the next one is the translation. So this one is x plus 2. And again, that's what I was just talking about a moment ago. Remember, we had to put that in brackets. And then finally, the last one, I mean, you see how horrendous this question is and how really similar all of the graphs look. But for the last one, we'll just need to put a plus 1. Imagine how long that would take you to do in an exam. I mean, you know, for the amount of thinking that's involved there, those graphs look awfully similar. So again, in order to do that, I would probably, to make this clear, this would be like a piece of coursework really. To make this clear, I would then say, well, what's happened to each of these points? Well, I've taken 1, 1 to be the point, a fifth 1. Okay, so would be 1/5 and then comma 1. So that would take us to this point here. That's the first move. And then we had the stretch of a factor of 2 in the y direction. So then we had a fifth, comma 2. And then we had, after that, fifth again. And then we're reflecting in the x-axis. So this reflection in y equals to 0 is going to give us minus 2. So that's our new point. And then after that, we have, it's horrendous, this question. Okay, we have this, and we don't have that. This goes back by 2. So back by 2 is now nearly minus 2. It's not, is it? It's minus 1.8. Okay, and then minus 2. So there's that. We take off 2 from a fifth, we end up at minus 1.8, minus 1 4/5. And then the final transformation is to add 1 onto the minus 2 there. So it's the minus 1.8 comma minus 1. There we go. That's the sequence of points which we've taken. And the book might have taken it in a slightly different sequence because, of course, we can switch around the order of these stretches and translations as long as you always do the thing that's happening in one direction. You're having your stretches before you're doing your translations. So you can do things in a slightly different order. I've talked about that already. Okay, right. Well, this is hellish. Okay, so let's have a look down then at next question. Moving on from that now. We have come to the final question here. I'm very happy about this. Example 39. So explain the transformations on the graph of f of x equals 1 over x to obtain the graph of the function. Hurrah, we've got finally one of these questions here. We basically need to put this in a reciprocal format, which is what I talked about after I talked about all of the combined horizontal transformations, right? So really early on, I talked about this. So we're saying, let's put this, what we want to do is put this in the format a over b x minus h plus a. We want to put it in the reciprocal format, and then we can make transformations from this. Okay, now remember how I suggested you do this is to force the same denominator to occur on the top. Now in this case we don't need to do any division by anything, we don't need to factorize out anything because we have the same amount of x on the top and the bottom. So actually this one's really easy because we can then force the x minus 3 there, and then we're going to need to have plus 5 to make x plus 2 there. And then we've got x minus 3 there, bracket and that. So left-hand side of this, when we split it up, is going to give us 1, and the right-hand side is going to give us 5 over x minus 3. So the transformations of f of x, this thing here, to f of 5 f of x minus 3 plus 1. Actually relatively straightforward, this one. You can do the translation followed by the stretch followed by the translation, but actually here I'm going to make it a little bit easier. I'm just going to say that this is a stretch in the y direction by a factor of 5, and then it's a translation by the vector, and the vector is going to be 3 forwards and 1 up. Okay, so 2 translations, 1 in the x direction, 1 in the y direction. Okay, so that should be done. Oh, that's a nice question to end on. So what does it say? It says shift the graph horizontally 3 units to the right. So they've done the x first, then they've done the stretch vertically by a factor of 5, and then shift vertically by 1 unit. Oh, they've said shift. You should say translate. Okay, so translate vertically 1 unit in the positive y direction. Okay, but as long as you've got your vertical stretch happening before your vertical translate, it's fine. Okay, right, well, thanks for enduring that one. I suggest that if you come up with, see any questions which are like the example you get in example 38. So if you see any questions like this, where you have to draw all of those functions, I really think that it's a skill to do it, but it's going to take you ages. So I think what I did, which is talking about doing each of your transformations on Desmos and then taking a coordinate point and following that coordinate point through all of those transformations, is going to be a much quicker way of getting quite a lot of understanding from that question. Okay, so let's just have a look. We've got 2R there. And what's coming up afterwards is the last exercise here. The last exercise looks like it's about more modulus graphs. more modulus graphs. And so it seems to be a bit of a mixture of transformations on this one. Okay, so that's to look forward to, and that's going to finish off this unit. Okay, thanks for listening, guys, and good luck with the exercise.